I will talk today about TDD, which means type-driven development, as you should know, I think. So quickly, I work at Clevercloud. We do IT automation, and just the marketing department asked me to say we do IT automation. What we do is we take your application and we make them run in production. So we restart them, we build them, monitoring, backups, every boring thing about ops is handled by the platform. And we support a few languages. So if you want to try it out, we can talk about it later. So I'm CTO there, but I wasn't born a CTO. Deep in my mind, I'm a functional programmer. And I haven't been a functional programmer all my life. I used to work a lot with PHP, and I switched to functional languages. Not because I wanted to sound intelligent or smart or stuff like that. Quite the contrary. In fact, I did that because I'm not a smart man. And I want tools that help with the dumb mistakes I do every day. That's why I switched to functional programming. Okay, so I will start with a simple example of how we can use types to improve the code. So let's say I want a simple HTTP endpoint. You pass it a number, and it adds 5 on it. So I can create an action. So all the examples are written in Scala. Normally it's readable and not too complicated Scala, so it should be quite easy to follow. So I have an action in my controller, and I get a map string of query parameters. It's HTTP, so everything is a string. So it's simple. I start to get the parameter called number. If it's not an empty string, I try to parse it into an int. And with that int, I can return this number with 5. So should work, right? So yeah, if I give it a string that represents an int, then it works. If I don't give it a parameter called number, then it's kind of a null pointer exception. And I can also give a string which is not a number, and then I have a number format exception because I couldn't parse it into an integer. So one solution is to catch all these exceptions. And as I call it, it's called Pokemon-driven development. You try to catch all the exceptions. And your code starts to look like this. So you get the parameter from the map. You check if it's there. And if it's a string, then you try to parse it with an int. And if it's not, then you handle the number parsing exception. Okay, so that was simple. Now I will try to make things a bit more complex. Let's say I want to add 2 numbers. And to do that, while catching all the exceptions and ensuring you don't have any runtime error, you end up with code that looks like that. For something that takes two strings, parse them into numbers, and add them. And the idea is the domain, the logic is completely hidden behind layers of defensive programming. And I don't know you, but me, I don't really like that. So let's try to take a step back and try to think with types instead. So the first insight we can get is that I get a map, I get a key, and I get maybe a value. I'm not sure, because the map does not necessarily contain value at the key I want. So we can have a new function which, instead of returning a string or no, returns me a maybe string. And similarly, from a string, I may be able to parse an integer, but not necessarily. If the string is a string of digits, then okay. But if not, I don't have any meaningful result. So I could define a maybe string and a maybe int. But since I'm using a language with generics, high-level feature, I can define an option which is parameterized by the type it contains. So either I have no value and it's none, or I get some and I have my value. So can rewrite my functions with parsing, taking a string and returning an option of int, and a method get on map, taking a value, a key, and returning an option of value. And then if I combine these two things, I can create getInt, which tries to take a value, and if it's there, tries to parse it, and if it's okay, then I have a value. Else, I have nothing. So by thinking with types, I was able to pipeline my operations, and instead of being in a reactive way of programming, and not reactive in a good way, I react to errors, then I think about the transformation and I'm able to change them. So my controller now looks like this compared to that. I think it's okay. So the idea there is to try to write code that is correct by construction. Like, you have to do these things in a way that creating an invalid program is not possible. And like, if you're trying to do something that doesn't make sense, then the compiler will say no. I don't know how many of you are used to programming in like dynamic languages, like Python or stuff like that. Every time I talk about it with mostly Python programmer, they say, oh yeah, your types are really interesting, but I have 100% test coverage, so I'm okay. And my point is not that tests are useless or you shouldn't use them. My point is that tests are really useful tool, but it's not a tool that does everything. And there is like a profound reason for that. Don't know if you know this symbol. It's called the existential quantificator. And in plain English, it means there exists. There is a value such as it does that. And that's precisely what types do, what tests do. There exists a value such as it works or it doesn't work. Let's say you have a function from integer to integer. I'm sure you've watched Philip's keynote yesterday when he talked about exponentials and function being exponential. So the number of function from int to int is, it's not that, it's 2 to the power of 32 to the power of 32. And it's a big number. I could try to like display it on my computer, but just displaying the digits will take forever. And if we are on a 64-bit architecture, then it's even worse than that. And even worse, let's say we try to test a function from string to string. Then it's practically infinite. Depends on the memory bounds of your machine. What I want to say is that testing can give you a proof only if it's exhaustive. And usually, when we program, the types we have a big number of value. And we can't test for every value. So what we would prefer is to be able to prove things for all value of my type. And turns out we can. There is an interesting result called the Curie-Howard-Lambda correspondence. And it describes the correspondence between type systems and logic. So with that correspondence, a type is equivalent to a property or a theorem. When you state a type, it's as if you're stating a theorem. And corollary is that when you create a program that is well-typed, that compiles and has a type, it's as if you've given a proof of your theorem. And the good thing with programs and compilers is that it's done automatically. And in fact, there is a branch of proof which allow you to, which let people prove things with something called a proof assistant, which is a compiler. They say, I want to prove this property, and then they type the proof, and the compiler verifies that each step is correct. And that's literally a compiler. And of course, I'm not saying you should all do formal methods on your code. Like maybe you're working on rockets or airplanes, and in that case, please formally test your code. But for web pages, it's not I'd say it's not a good investment to formally prove your cat pictures website. So the good thing is that when you program with by really using types, you're not writing a formal proof, but the code you write has the same shape as a proof, and we can call this code a code that is provably correct. You don't actually write the proof, but the code is shaped in a way that it would be feasible and quite easy to write proof. And that's very good. So if we are able to have a program that compiles, then it proves a property. So the next step is that, yeah, if my type is int, then I've proved that the value is an int, and it's not that interesting. So the next step is to have an expressive type system. If you're able to have expressive types, then you have expressive properties. And the more the types are precise and close to your domain model, the more it helps you. One thing that helps a lot in a type system is languages where everything is an expression. Because if everything is an expression, then everything has a type. Then you can prove things about stuff. And a good example of that is that you are able to type control structures. Like in languages like C or Java, let's say an if block is just a block. The compiler cannot check anything in it. But in other languages where if are expressions, then the compiler can prove things. For instance, for an if block, it will check that the two branches are homogeneous. They return the same type of value, stuff like that. And it's the same with lists. So with that, your control structures are typed. So your compiler is able to verify what you're doing, not with just data, but also control flow. And it's really, really powerful. And it allows you to avoid stupid mistakes. I don't know if you remember, don't remember if it was OpenSSL or in the Apple SSL implementation, certificate verification was bypassed because there was a duplicated line and it was always jumping to the fail label, even though it shouldn't. And everybody said, yeah, of course, they didn't put braces on our if block. Amateurs. But the issue is not the missing braces. The issue is that the compiler is not able to understand what you're trying to do with control. So that's the first feature that will help you a lot in typing your programs. I've shown you maybe or option. It's a way to tell the compiler that a value may not be there. And it helps you avoid null pointer exceptions, which is quite good. There are lots of things. Non-empty list, it's a list that's guaranteed to be not empty, which comes in handy really, really often. So you can always take the head of the list and it will never blow up. You can use something called validation, which contains either your value or a list of errors. It's really, really useful when you're like validating forms or user input more generally. You can do lots of things. If, let's say, you have a user that needs to input an email address, and you check it once that the email address is valid, then either you can like pass strings to the rest of your programs, and in command say, yeah, this string is an email address, it must have been checked, but what if it isn't? With new type, you can create a type that is exactly the same as a string, but that will carry out the proof that it has been verified. And the best thing with that is it's erased at the compilation. Once the compiler has proved your code is correct, then it's as if you've used a string for runtime performance. So it's really useful. And a small thing I like, it's called tag types. Small example, there was a Mars probe that crashed because there were two teams, one working with miles and the other working with proper units. And it crashed because there was a discrepancy. So with tag types, you can tag a value and say it's an int representing a value in meters. And then the compiler will tell you if you try to mix it up without converting. So it's really useful. And as with the new type, it's erased at compilation. So it's a free check. At runtime, you don't pay any cost. And yeah, now with Rust, memory management is handled by the type system. The type system will make sure that you don't double free your memory, stuff like that. So you can do a lot of things with the type system. And also resource management. It's the same thing in Rust. You never have to close resources. When the handle goes out of scope, then it's closed automatically. And the compiler makes sure that it's closed exactly once, which is super neat. And like a guarantee you don't have currently in Haskell or Scala, for example. So these all are interesting tools, but I will talk about something a bit more profound and more important when it comes to being type safe. And this tool is Parametricity. If you're coming from the Java world, it's called generics. And you may have seen it and discovered it as a way to reduce duplication, like to have code reuse. But it's not the most important characteristic of generics. The most important characteristic of generics is that you don't make any assumption on the type you parameterize over. You don't know anything about it, and since you don't know anything about it, you can't do stupid mistakes. Small example. This function, it takes an A and it returns an A for all A. I don't know anything about A because it needs to work with any type. The only sensible implementation for this function is to return the value that was given. Because I don't know anything about A, so I can create a value of type A out of thin air. So by looking at the type, I know there is only one sensible implementation. Same thing for that. I take a function from B to C and a function from A to B, and it returns a function from A to C. The only sensible interpretation is to implement it with function composition. No other implementation makes sense. So these two examples are really neat because there is only one sensible implementation. But even though in cases where you don't have only one implementation, and it still helps you. Let's say I have a function called reverse. It takes a list of A, and it returns a list of A. Of course, there are many implementations possible. It can return always an empty list, return the list that was given, maybe reverse it, maybe do other permutations. But I can still have information on its behavior. For instance, I know that if I call it with an empty list, then I will get an empty list back. I can create values of type A, so I can create a non-empty list from an empty list. More generally, I'm sure that if the reverse or if the return value contains a value, I'm sure it was in the original parameter. And that's really important because it allows you to drastically reduce the number of tests because you can prove stuff. And there is actually a paper called Theorems for Free, written by a guy called Phil Wadler. Maybe you've heard of him. And basically what it does is say, given a type of function, if it's parametric, I will be able to derive theorems on its behavior. And it's for free. I don't have to, don't show me the source code. Just by looking at the types, I can guarantee you it will work this way. For instance, let's say I have a list type with filter and map operations. By applying theorems for free, I know that if I map a function and then filter it, it's the same result as if I filter before mapping. Just by looking at the types, not looking at implementations. So it's very, very powerful. So it's very good, but, it's always a but, you need discipline. Because there are features in programming languages which break the guarantees provided by parametricity. So if you use them, then you throw all this information out of the window. The first thing you need to do is to avoid using null. It's common knowledge, like using null should be avoided. And the common reason for that is people say, yeah, if you don't use null, you can't have null pointer exceptions. Yes, I will try to show you another way to think about it. So, we've seen that a type is equivalent to a property. So, null, what is it? Null is a value that can inhabit that, like every type, you can put null and it will compile. So null can inhabit any type. If we move over to the logic side of the correspondence, what it means? It means null is a proof that can prove everything. And a logic system in which you can prove everything is not really interesting because everything is true, everything is false. It's not useless. And for the same reason, you shouldn't use exceptions. It's the same as returning null. If you throw things, then you're not forced to return anything. Okay, so that living without null and exception is really manageable. Many languages do that, and it's quite okay. Next one is maybe a bit harder. You don't want to use reflection because reflection means inspecting the type, and it means breaking the principle of ignorance. Let's say I have a function that takes an A and returns a string. Since I don't know anything about A, the only sensible implementation would be to return always the same string, regardless of the input, because I can't do anything with the input. If I use reflection, then I can provide other implementations. And that's an issue, because when I see a function from A to string, I'm expecting to see a function that returns always the same thing. For the same reason, you can't use toString equals hashcode because they are defined for every object. So I can always call toString on any value, and that breaks parametricity too. Side effect is the same. If you do side effect, for instance, reading from the environment, then it will do bad things. But there is a good news. There is a paper called Fast and Loose Reasoning is Morally Correct, which says that it's not too bad if your language actually supports these bad features. As long as your team is disciplined and restrains from using that. In practice, they did a study on programming teams, and it showed that it was more or less the same as the language not having those features. Like, programmers were disciplined and didn't use the features, and then everything was working well. So it's a good result. So going back to type-driven or type-directed development. There are a lot of type apologists or type evangelists saying, yeah, you should use types for everything, and if you're not using types, you're not a good professional. It's a bit too extreme. Types, they are not a silver bullet. There are other tools that complement types and are really useful. But they are really, really, really helpful. Types are a really powerful tool. And it's too bad if you don't use it. You can program and create interesting programs without using types. But you're missing out on really, really important tooling. First thing is that it brings you confidence. I can go back on the code base I haven't touched for months, and I go back to it, and it works. Because I don't have to put everything in my head. Again, I can change stuff, and if it compiles and the test passes, then it's okay. It also allows modular thinking, because when you're implementing a method, you're just looking at its type, and you forget about the outside world. Since every information is carried in the type, then you can forget the rest of the world and just work on your function. But that's an issue I have with saying you should use types because it will prevent errors. It's true, of course, but it's just a little bit of what types can do for you. For me, the biggest help with types is that they help with structure. When I create a program, I've been taught to use analysis and to break my problem into smaller problems. And I've done that with pseudocode, like syntax that helps me write it on a sheet of paper, but it's just me and a sheet of paper. No tool is helping me saying, yeah, this is good structure or this makes sense. With types, I can actually do that. I can write the type of the functions, and then the compiler will tell me when I try to assemble them if that makes sense. Let's say I have a list of input and I have a list of output. I can call map on it and pass it a method that transforms an input into an output. And I don't need to provide the implementation of this mapping function right now. I just say it takes an input and returns an output. And the compiler will tell me, yeah, you can map this function over this list. That makes sense. OK. And I don't have to code everything to get interesting results. Another thing is that type checking is just a part of compilation. Compilation is providing a binary from your source code. Type checking is a step. Usually it's a step that bundled with other stuff. But in some languages, type checking is actually a separate step. So for instance, in Idris, you can just type check your code and not compile it. So when you're working, it's really fast because it just type checks and it doesn't go all the way to generating binaries. And it's really efficient to work this way. And we can do a thing called hole-driven development. I think that there is a conference, maybe right now or maybe later, about using holes in Haskell. The good thing is that you don't need any language support to do that. You can just trick the compiler into telling you what you want to know. I create a new type called hole. It doesn't exist. It can't clash with anything. And I will try to type a function. And I will put this special value in place of the implementation. And then the compiler will tell me, I expected a function from A to C, but you gave me a value of type hole. I don't know. And then you write your code step by step. And then the compiler helps you refine the implementation by telling, yeah, what you've done is good, but I still lack an implementation of this type and stuff. And step by step, in a very mechanical way, you end up with a proper implementation. And the compiler helps you to write it. So, you all know test-driven development, red-green refactor. You write test, it doesn't pass. You make the simplest code that makes the test pass, and then you refactor. With type-driven development, it's type, define, refine. You create a type describing what you want to do. You define your implementation, and then you refine the types to be more precise. It comes from a book called Type-Driven Development with Idris, which I heartily recommend. So, type are cool because they make communication easy. Of course, with machine. When we compile a program, we're talking with the compiler, and types is a really powerful language to discuss with the compiler. It's also good with tooling because the compiler knows stuff. So you should really learn Haskell type syntax because it's a really simple syntax which allows you to describe types. So this is a function from A to A for all type A. Okay. This is a function from int to int. So if the type starts with a lowercase letter, it's a type parameter. If it's with an uppercase letter, it's a concrete type. In Haskell, we don't have functions of multiple arguments. We have something called curate function, so you will see that everywhere. You can think of it as a function taking an A and a B, returning a value of type A. But you can also think of it as a function taking one A, and returning a function that takes a B and returns an A. It's called, describing functions like that is called currying or Schoenfinkling or fragging. And giving values one by one, it's called partial application. It's very useful to compose and create small functions on the go. Another thing you need to understand is that you can put constraints. This means for all A, provided that I can provide an order for A. So provided that I can compare two values of type A. And it gives me intent. How many of you know Google? Okay, so for the others, you will be mind blown. Let's say I want a function to remove duplicates in a list. Let's try to imagine its type. Its type would be a list of A to a list of A, provided that I can compare two values for equality. And I can type just that into Google, and it will give me the result. And it's called nub. I think it means remove duplicates in English, but it's not an easy function to know. I can do the same. I have a list of maybes, and I want a maybe of a list. Like if every value is defined, then I want all the values. And I can type that into Google. And the best way is that Google will actually give me a better type. It says, yeah, you've asked about maybes, but I've got this function, so it works for any monad. So it's even better. So talking with computer is cool, but writing programs is also talking with humans, and foremost talking with humans. And that's a very good thing. Most of articles about programming and types, all the examples are written in Haskell because the type language of Haskell is really concise and easy to understand. I said it, I say it again, you can prove everything with types. There's a limit to the expressivity of the type system, and that's not a problem. Like this function reverse, I can prove its behavior with types only. But what I can do is to write tests that prove it. And the good thing with those tests is that it works with input that I don't provide. So you still get the formal view of thinking. You think about properties, but it's not a real formal. It's not proved structurally. But the test system is doing the hard work for you. So there are libraries called type check and stuff like that, quick check, sorry, that do it for you. It's still property reasoning, not proven, but still the same way of thinking as with types. And it's perfect with edge cases or testing specification. So what you should do, start with types, try to prove as much as possible with types. And when it becomes unwidely, then you go to a property test. And then you can use unit tests for pinning, regression tests, stuff like that. So in practice, you start by laying out the function types. That's the most important thing, and that's where your business logic is, the transformations of value in your program. Then you write property-based tests to assess more properties about your transformations. So you end up with operations and laws on these operations. And if you want to sound smart and sound mathy, you say, yeah, I got an algebra. But it's just function types with properties, nothing more. And then you can start figuring out data structures and doing the implementation. But it's the third step. Like committing to a specific type is way late in the process. You can test, you can unit test for regressions if you want. So to recap, types, they are a safety feature, and I think that the main way we talk about it right now, and I think it's a shame, because the safety they provide is cool, but it's very little compared to what they also provide. For me, it's a tool to reason at a very high level, to reason about how to decompose my programs, how to analyze my problems. And the best way is that I can describe high-level things, and the compiler will check them for me. which is way better than just writing stuff on paper and hoping everything is okay. And most importantly, types are really important communication tool because it's really concise, it's really dense, it packs a lot of information in a really small language. And you are able to talk about concepts really complex and advanced with other people without having to read implementation. Like, you can just scribble out a few types and use it to communicate with your colleagues. And you don't need to sift through thousands of lines of implementation to try to understand the behavior of your system. With types, you can specify a lot of things. So please use them. Okay, to conclude, if you want to learn more about types, there are two really important books. So the first one is called Types and Programming Languages by Benjamin Pierce. So if you want to know about type theory, it's where to start. The other one is Practical Foundation for Programming Languages by Bob Harper. In that book, he uses type theory to unify lots of things. So these two books it takes time and it's not an easy read. Like, you need to commit to it. If you want maybe more practical introduction to this kind of programming, in Scala there is functional programming in Scala. We call it the Red Book. The Red Book with Scala on it by Runar Bjarnason and Paul Chiusano. Very good and very detailed. Another way to look at it is Functional and Reactive Domain Modeling by Debashish Ghosh. What it does is that it describes how to do domain-driven design, which is usually illustrated with object-oriented concepts. You can do the same with functional programming. And if you do that, you end up doing designing your algebras. So very, very good book. Lots of concrete examples on how to design your systems. Highly recommend it. If you want to prove everything in types, you can with language with dependent types. Type-driven development with Idris is very, very good book. So if you want to discover Idris, which is a very nice little language. And also, you can try Rust. It's good. Rust is good because I always thought type went hand in hand with functional programming. And with Rust, I discovered that you can do imperative programming and still have the compiler help you. And that was really an eye-opening lesson for me. And I think there is a session about how to use Rust for functional programming. So I encourage you to attend this session. And I'm always okay to talk about Rust if you want. I'm part of the Rust evangelism task force. Okay, I think that's all. So if you have questions, we can go.